Hello students. Today in this class let us discuss about the basis path testing. Okay. We are discussing the other topics in the past path testing in the earlier classes, right? That is the path coverage matrix we discussed in the last class. Before that we discussed about the DD path testing, etc. So basis path testing is one addition to those path testing algorithms, right? And these are all the techniques of white box testing, where actually we test the traversals in the program flow graph. Okay, that is whether the internally program is correct or not. Okay, right? This is what the white box testing does. It basically tests the internal structure of the programs. So basis path testing is one of those different methods which have been proposed for a white box testing. Okay. Now it was proposed by a scientist whose name is McCabe. Okay, Thomas McCabe in 1982. Okay. So it is based on the vector space. A vector space is where you have vectors and operations which are defined on the vectors like multiplication and sums. Together they are called as the vector space. Vector is something which has direction and the magnitude, right? So this is what mathematical background that you require. So every element in the vector space can be expressed as a linear combination of basis vectors. So basis vector is basically a subset of the vector space. So basis vector, those vectors whose linear combinations gives rise to every possible vectors in the vector space. That is what a basis vector is. Okay. So one example, so you can take out that a Euclidean tree space has three basis vectors. So Euclidean tree space has a basis vector defined by the x direction 1, defined in the y direction 1, defined as the z direction 1. So in combination you can find out all other vectors in this particular vector space. Okay. So the hope from this is that the program graph can be thought of as a vector space. So because in the program flow graph we have the directed lines, the edges, so we can consider them to be the thought of as the vector space. There should be a set of basis vectors. Okay. So testing them test many other paths. So since we can derive all other vectors in the vector space by using the basis vectors. So if we have the test case derived for those basis vectors, then we can have the most of the test path covered. Okay. So that is the hope with which the algorithm has been developed. Now basis vector testing has actually 4 parts. Okay. So these 4 parts are compute the program graph. Okay. That is, we know how to compute the program graph. In the previous classes we have discussed that. The program graph that we have computed for the triangle problem that we have discussed, right? So then calculate the cyclomatic complexity. I'll come into what is cyclomatic complexity. Okay. So calculate the cyclomatic complexity. Select a basis set of paths. So you basically select the basis set, okay, basis vectors, and then generate the test cases for each of these paths. Okay, for all those basis paths. In general, we call this as the basis vector, but since it is related to the program graph, we call it the basis path. Okay, basis set of paths. Now generate the test cases for each of these paths. Okay. So this is the second point is actually in math the basis span an entire space such that everything in the space can be derived from the basis elements. Just for your understanding, I have included this particular line. Okay, because basis is the minimal set of vectors in the vector space from which you can generate the entire path set. So cyclomatic number of a strongly connected graph is the number of linearly independent cycles. Okay. To generate the cyclomatic complexity, the second point here, you need the cyclomatic numbers. Okay. So cyclomatic numbers are what? Are actually the number of linearly independent cycles. If inside the graph, if you find cycles, the number of linearly independent cycles give you the cyclomatic number from which you can derive the cyclomatic complexity. Given a program graph, we can always add an edge to the from the sink to the start. Sink is the end node. Okay. So if you have a program graph, any program graph, okay, you have drawn from the program, you can add an extra edge from the end node, that is the sink node, last node, to the start node, the first node. Okay. And with that addition, it becomes a strongly connected graph. Okay, to make the graph strongly connected, there are advantages of creating the central strongly connected graph. So for every basis path testing, for this particular technique, we always add an extra edge from the sink node to the start node to make it strongly connected graph. Okay. Cyclomatic complexity of a strongly connected graph is provided by the formula. This is the formula for calculating the cyclomatic complexity. Now, what are the components of this formula? That is E minus N plus P. What is E? E is the number of edges, N means the number of nodes, and P means actually the number of connected areas by P. Okay. So different regions which comes under those independent cycles, they are calculated as P. Okay. So P is basically the number of the connected areas by P. Okay. So number of connected areas is represented by P. So the formula for deriving the cyclomatic complexity is E minus N plus P. You have to remember this. Okay. Since all other program execution paths are linear combination of basis paths, it is necessary to test the basis path. So when you in the path program flow graph, okay, all the other paths can be derived from these basis paths. Okay, so it is important to derive the test cases for the basis path. So next few slides will show actually the Macbeth's original example. Okay, the original example he used to define his this basis path testing mechanism. So so suppose this is the original graph where you have how many nodes? 7 nodes. How many edges? 10 edges. Okay. So but this is not a strongly connected graph. Okay. So you have this cyclomatic complexity calculated as 5. Okay. So because we are considering the 2 regions to be here, one is this independent path and this one is another path. So it makes one particular, there are 2 regions for which it comes as 5. Now in this case, the connected graph, we convert that particular graph to a strongly connected graph by adding this particular edge. This is an extra edge we have added to make the graph strongly connected. Okay. Now the cyclomatic complexity, there is no difference actually, because with the extra addition, number of edges become 11, from 10 it will become 11, nodes remain the same, 7, and the region becomes 1. So the cyclomatic complexity that you get is 5. Okay. So that is derived as strongly connected graph from the original graph. Now coming to the basis path. Okay, this is just an pre-task that you have to do to derive the basis paths. Okay. So to derive basis path, we must know certain things, like an independent path is any path through the software that introduces at least one new set of processing statement, okay, or a new condition. So when we have a node here and a path over here, and again suppose node, and we have a two different paths over which it is being calculated, and suppose it merges into one here. Okay, now, and suppose there is this is the sink. Now an independent path, this path, suppose this is 1, this is 2, this is 3, this is 4, 5, 6. So what is an independent path? The independent path is any path through the software that introduces at least one new set of processing statement or a new condition. Okay, so while you go for here 1, 2, 3, 5, 6 is independent of 1, 2, 4, 5, 6 because 3 and 4 are distinct, right? So it is new set of processing statements are there. Okay, so both these paths are independent of one another. Now to find the paths, McBake developed a procedure known as the baseline method. He has developed a certain, rules for developing to find the independent paths. Okay, so the procedure works by starting at the source node. So you start at the source node, and then from the source, the leftmost path is followed until the sink node is reached. Okay, so what he proposed is that you should start with the leftmost path till you to develop the path actually which goes from the source to sink. Okay, so he preferred that always leftmost path should be traversed. So here what is the leftmost path here? So you go for the A, B, C, Z, right? This becomes the leftmost path. Okay, so A, B, C, Z becomes the leftmost path. So you start from the leftmost path. Now we then repeatedly retrace this path from the source node, but changes our decision at every node with the out degree 2. So we repeat this leftmost path approach for every node, okay, from the source node, but changes our decision for every node where the out degree is 2. What is the out degree 2? This is the out degree 2, where the decision has been taken, one goes on the other side, another on the other side. So we have the out degree 2 here. Okay, so starting with the decision node lowest in the path. So when we are looking for those out degree 2 nodes to have the distinct path here, we must go for the lowest node which does such a decision. That is I'm just showing the example that the next path for this McBath, for example, is for the next path for this problem, his example is, because see, when it goes from A, B, C, Z, this B is also of the out degree 2, whereas C is also of out degree 2, right? Because from C you can go to Z, from C again you can go to B. So out degree is 2. From B you can go to E, but from B you can go to C. But according to McBath's proposal or McBath's method that the method he developed, he says that the lowest node which takes such decision where out degree is 2, that should be taken first, considered first. That means that is starting with the decision node lowest in the path. Okay, that means you must change the path at every decision node which is greater than where out degree is greater than equal to 2, but the lowest node should be given the first preference to take the decision. Then comes the higher nodes. Okay, so for that reason, our next path in this case will be A, B, C, B, C, Z. So A, B, C, B, C, Z is which path in this graph? A, B, C, because there is another edge tree here. So you go to B, B, C, and then Z. So we are taking the new decision taken at the C. We are following the other path to show the tree. Okay, path taken by 3. So at least one traversal has to be there. So before B, we are giving preference to C according to make path. So next basis path is this path, that is A, B, C, B, C, Z. Okay, so B, C appears twice there. B, C, B, C, Z. Okay, A, B, C, B, C, Z. So then the third path will be, because after that C node, we have to give the decision, because the B node also is of degree 2. So we have to split that node, that we have to take the other decision path in the B node. So here it is the third path is A, B, E, F, Z, as the next lowest decision node is B. So the next path taken is A, B, E, F, Z. That is A by edge 1, then from B it takes edge 5 to E, from E it takes edge 8 to F, from F it takes the edge 10 to reach Z. So this path becomes the third path. Okay. So using this technique, he has developed how many basis paths? So the basis paths are 5. See, P1 is A, B, C, Z. Then comes P2, where the C node is taken as the node where you are generating the other basis path. So that is A, B, C, B, C, Z. Then takes the B, A, B, E, F, Z. Then takes A, that is A is the highest one. So A, D, the other path, A, D, F, that E, F, Z will be taken. Okay. And finally, the rightmost one, A, D, F, Z, is taken as the last basis path. Okay. So these are the basis paths which are taken. Resulting basis paths are the 5 from this graph. Okay. So this now forms the basis set of paths for the graph, right? So in theory, if we allow for the basic notion of scalar multiplication and addition, we should now be able to construct any path from our basis. So since we have the basis path available with us, now in theory we can use the scalar multiplication and addition to generate any other path which can be derived from the basis path. Okay. So let us attempt to create a sixth path. What is that sixth path? A, B, C, B, F, Z. Okay. So A, B, C, B, F, Z. Let us look at that particular graph. A, B, C, then going to be E, F, Z. Okay, the path is traversing from A, B, C, B by taking the edge 3, then E, then F, then Z. So this is the path. Okay. So with this path, how this path is derived from the basis path? This is derived from the basis path P2 plus P3 minus P1. So this P2 is the second basis path plus P3 and then minus P1. This equation means to concatenate the path 2 and path 3 together to form the path ABC, BC, ZA, BE, FZ. Okay, and then remove the 4 nodes that appear in the path 1. Okay, so what we have, just look at this one. We have, by, as I told you, with the scalar multiplication, addition, etc., you can basically form the other paths using the basis path. Now the basis path is, in this particular path, what is the path? You just see A, B, C, B, E, F, Z. Remember, A, B, C, B, E, F, Z is not the basis path. It is a path derived using basis path. Okay, for testing. Now this basis path comes from the P2 plus P3 minus P1. Okay. Now let's go to the basis paths. Now what are the basis paths? The P2 is A, B, C, B, C, Z. Okay, write down A, B, C, B, C, Z. What is P3? A, B, E, F, G. A, B, E, F, Z. Okay. So now remove the nodes which are in path 1, that is P1. So that is the A, B, C, Z. Okay, A and Z. So we are removing these 4 and we get this one. It is not mandatory that only this has to be. This path from here, this is the path to get from here. We are just removing this middle part that is actually part of A, B, C, Z. Okay. So BC. So those, because there are some nodes are there twice. So we are removing those nodes which are there in the path P1. So remove those path P1 and you get a new path. Okay. So that is, this is a arbitrary equation. Similar equation you can derive and you can get a new path here. Okay. So we clearly now have a basis which in theory can be rigorously tested, thus verifying all other paths constructed from each element. Okay. So we have a basis here, so which in theory which can be rigorously tested from the basis, and then we can have we can have the paths which can be tested rigorously. Okay, verifying all the paths constructed from each elements. Of course, this Z cannot be removed. This has to be there because this has to be source to sink. This A has to be there. This Z has to be there, right? So this Z has to be removed from here. Okay. So that way, those nodes, which were there, which comes in that particular minus part, that has to be removed. Okay. So for this path is incidence, we can create a table. You can say path is table, and we can see which nodes are incident in how many numbers. Okay, that is the out degree in degree. So for that, for out degree, you can see A, B, C, Z. Okay, so which the A, B, C, Z traverse through which particular edges? How many times? The edges E1. These are the number of edges in the particular graph. E1, E2 up to E10. Okay, these are the paths. Okay, up to this they are the basis path, and these are the 2 other paths which are derived using the basis path. Okay, now for this, the ABCZ you traverse through E1, E4 and E9, right, to get the sink node G from the source node A. Similarly, for the basis path P2, you traverse through E1 once, E3 once, E4 twice, and E9 once to get the sink node G from the source node A. Similarly, for the path P3, you traverse E1 once, and E5 once, and E8 once, right, and E10 once. Similarly, that way it goes on, and this path which has been derived, I have already explained this example, that is P2 plus P3 minus P1 gives you this one, example 1, and you traverse the path for this particular path which has been derived using the basis path is E1 edge is traversed once, E3 is traversed once, E4 is traversed once, E5 is traversed once, E8 traversed once, and E10 traversed once. Okay, and there is another path, example path, which has been derived using the basis path. What is the formula used here? The equation is 2p2, right? It is the 2p2 minus p1. Okay, so you consider the p2 twice and then remove the p1s. Okay, you get this particular set of nodes, that is BC, BC, BC. You get BC, BC, BC and G. Okay, so P2, as you can see, you just concatenate it twice, that is A, B, C, B, C, so G, A, B, C, B, C, G, A, B, C, B, C, G, so it makes it 2p2 minus p1. So if you get minus p1, what is p1? P1 is A, B, C, G. So remove one BC from here, remove this A, okay, and this B and one of the BC. Okay, so you get this from here, from this part, you get A, BC, BC, and from here, this part left out, so you get BC, Z. So that is the path that has been derived from the basis path. Okay. So there are some problems also with the basis path technique, always not very suitable. So, so these are the different problems, like what is the significance of path as a linear combination of the basis path? How significant is the path that is derived as the linear combination of the basis path? What do the coefficient means? What does a minus sign means? Okay. So in the path example 2, that is 2p2 minus p1, should a tester run path p2 twice, or then not to do the path p1 the next time? Actually, in theory, it runs amok. Okay. Is there any guarantee that the basis paths are feasible? We discussed about feasibility and infeasibility path. What is an infeasible path? Where given the inputs, you don't find the actual test. You cannot do the actual testing using the probable inputs. Those paths are called as the infeasible path, right? So we discussed in the last class. You can see my lecture in the last class about this one. So here, is there any guarantee that the basis paths are always feasible? Is there any guarantee that the basis path will exercise interesting dependencies? Okay, so these are some of the questions actually regarding problems with the basis path. So for the triangle problem that we have discussed earlier, there are the basis path generated are this, you know, the triangle problem using that first the leftmost path, this one, the main line, then flip that 9, that 9 on 9 there, you get a flip there, and you get another basis path. Then the third basis path you get, you know, and flipping at the 13. There is another basis path you get by flipping at the 14, okay, and then ultimately by flipping at 16 you get another basis path. Okay, so these are some of the basis paths which are generated from the triangle problem. Pros and cons of the basis path Macbeth's work. Okay, the issues that linear combination of execution paths are counterintuitive. What does 2p2 minus p1 really mean? Okay, how does the baseline method guarantee feasible basis path? Whether how that already we have discussed the problems. That is, how does a baseline method, that is the basis path, actually guarantees that these paths are feasible? Okay, those answers are not available. That is the drawback. Given the set of feasible basis path, is this sufficient test? Just feasible basis path, if we derive just a set of feasible basis path, is this sufficient to test? Okay, but there are some advantages. That is why this algorithm has been discussed. The advantages like Macbeth's approach does address both gap and redundancies. Okay, so because there are, you know, those gaps and redundancies are being discussed there. Essential complexity leads to better programming practices. So Macbeth proved that violation of the structured programming constructs increases the cyclomatic complexity and violations cannot occur singly. Okay. So violations are, if there are some violations of programming structured programming constructs, it actually leads to increase of the cyclomatic complexity. Okay. So those are actually detected. So that is one very important advantage there. And the violations cannot occur singly. Okay. So these are some of the advantages which are from the MACBA. So thank you for patient hearing of my lecture on this BasisPath testing method. Okay. If you have any doubt, please don't hesitate to ask me. Okay. That is very important because until and unless we discuss the doubts, it will be very difficult actually to understand the problems for me. Okay. Because we have to know, I have to know where you are facing the problems. So please be open up and discuss openly with me. Okay. That is, you can always send a message to me. Okay. To discuss, I am always available. I can deal with your problems using the Google Meet. Okay. So thank you for this listening to my lecture. Thank you.